Okay, so we had been talking about deducing molecular geometries by VSEPR theory, valence shell electron pair repulsion theory. And we had gone through the first 2 points of this handout on determining the geometry. The first step is to draw the best Lewis structure that you can for the molecule. And the second step is to figure out the substituent number on the central atom, which you do by counting up the total number of bonds and lone pairs around the central atom. Once you have determined the substituent number, then you turn to the back of this handout and you choose the geometry corresponding to the substituent number that you determined from step 2. So the back of the handout, if you print it out, you can just flip it over. Otherwise, you can scroll to the next page. Here we have the substituent number, and we also have the hybrid orbital designation, which I'll talk about in a future lecture. For now, I just want to focus on the substituent numbers for the central atom. Okay, so every title in this table here corresponds to the central atom. So the substituent number and the number of lone pairs on the central atom in whatever molecule it is that you're talking about. So I want to go through this table kind of slowly, and if I zoom out, you can see that we're really only talking about substituent number. So I want to start with the substituent number of 2, sorry, not 1 through 6, 2 through 6. I want to start with the substituent number of 2 and then carry on for through substituent number of 6 around the central atom. So looking at the first row, when the substituent number is 2 and there are no lone pairs around the central atom, for example, in carbon dioxide here, then you have a linear geometry around the molecule. Now remember, this is all based on electron pair repulsion. And what that means is that the electrons involved in these two double bonds want to be as far apart from each other as they can be in space. And you can't get any further apart for two sets of electrons, two regions of electron density, than 180 degrees. So they want to be 180 degrees from each other around that central atom, as far apart as they can be. And this results in a linear geometry. So when you have a substituent number of 2 and no lone pairs on the central atom, you just get a straight molecule with a linear geometry. Now, if there's one lone pair and one bonding region, then you just have a diatomic molecule that is also straight, and we just call that terminal. All right, so in the next example, let's look at what happens when we have a substituent number of 3 on the central atom. For example, in this molecule here, you have carbon bonded to oxygen and 2 chlorines. Now, in that situation, you end up with a trigonal planar geometry. Now, in a perfect situation, your trigonal planar geometry, okay, so here I'm showing you some kind of slightly more space-filling molecules. Your trigonal planar geometry would look like this: a flat molecule with bond angles equal to 120 degrees. So this is trigonal planar. Planar means flat. So the molecule is actually flat, and it's trigonal because you kind of have the 3 terminal atoms pointing to the points of a triangle. They want to be 120 degrees apart from each other because that's as far apart as they can be from each other in 3-dimensional space. In a situation like this molecule here, the double bond takes up slightly more space than the single bonds, simply because the double bond has more electrons in it, so they need slightly more space. So in this particular molecule here, this bond angle is going to be slightly greater than 120 degrees. And what that's going to do is squeeze this bond angle so that it's just going to be slightly less than 120 degrees. So that's the first of the kind of little exceptions that you should um, keep in mind. Double bonds take up more space than single bonds. And triple bonds would take up more space, right? So the more electrons you have in the bond, the more space they require. So double bonds take up more space than single bonds. Okay, so that squeezes in this bond angle slightly, so it's a little bit less than 120 degrees. Now, if you have a substituent number of 3 and you have one lone pair on the central atom, like in this NO2 minus ion here, in that situation, you end up with a bent geometry for the molecule. The molecule is bent because the lone pair takes up space. Okay, the lone pair takes up space just like a bonding pair. It requires its own region of space. And in fact, lone pairs actually take up more space than bonding pairs. So that's sort of the second little addendum to the rule. Lone pairs occupy more space than bonding pairs. So what that does effectively is it squeezes this bond angle so that the bond angle is going to be just a little bit less than 120 degrees because that lone pair takes up more space. And you can imagine, the lone pair is kind of centralized on that central atom. There's no other atom that it's bonded to, so it's going to take up slightly more space than a bonding pair. Okay, so the best we could say is that that angle is going to be slightly less than 120 degrees. And let me try to make my handwriting a little bit less horrible so you can see that. All right, so what happens when we have a substituent number of 4? For a substituent number of 4, if we have no lone pairs on the central atom, we get what's called tetrahedral geometry. Now our molecule is no longer flat. In order for those 4 regions of electron density to be as far apart as they can be from each other in 3-dimensional space, they are pointing to the corners of a tetrahedron. And the bond angle here is going to be 109.5 degrees. What this looks like in 3 dimensions, here I'm going to just show you the structure here. This is the tetrahedral geometry kind of showing you with shadows the 3-dimensionality of it. You see how this bond angle is slightly bigger than a right angle. That's because the angle is 109.5 degrees exactly. So all of the bond angles in a perfect tetrahedron are going to be 109.5 degrees. So that's true for, any of these bond angles around that tetrahedron. So we can see that example here in the ammonium ion with the perfect tetrahedron. If we have a lone pair on the central atom, so we still have a substituent number of 4, but one of the regions of electron density is a lone pair, the resulting geometry is a trigonal pyramid. And that means that, these 3 chlorines would kind of be the bottom of the pyramid, and then you would have the electron density occupying its own space. Now, because lone pairs occupy more space than bonding pairs, that's going to compress these angles so that they're going to be a little bit less than 109.5 degrees. Okay, and again, that's because the lone pair on the central atom occupies more space than the bonding pairs. Okay, so those angles are going to be a little bit squeezed in. Finally, if you have a substituent number of 4 and 2 bonding pairs on the central atom, like in water, you get a bent structure. So the bent structure in water comes because the lone pairs occupy space. And this bond angle is really compressed. Actually, in water, the bond angle is 104.5 degrees. So you can see exactly how compressed it is from the 109.5 degrees you would have in a perfect tetrahedron. Okay, in the next lecture, I'm going to talk about substituent numbers of 5 and 6.